Here's a simple game. You can play it with just a pen and paper. Pick a number. Any whole number you want. If the number is even, cut it in half. Divide it by 2. If the number is odd, multiply it by 3 and add 1. That's it. Those are the only 2 rules. Now, you take your new number and you do the same thing. You keep applying those 2 rules over and over again. Let's try it with the number 6. 6 is an even number, so we cut it in half, we get 3. Now we have 3. 3 is an odd number, so we multiply it by 3 to get 9 and add 1. That gives us 10. Now we have 10. 10 is even. We cut it in half, we get 5. Now we have 5. 5 is odd. Multiply by 3 is 15. Add 1 is 16. Now we have 16. 16 is even. Half of that is 8. Half of 8 is 4. Half of 4 is 2. Half of 2 is 1. Once you get to 1, something interesting happens. 1 is an odd number, so you multiply by 3 and add 1. That gives you 4. But we've already seen 4. From 4, we go to 2. From 2, we go to 1. Then from 1, we go back to 4. We are now stuck in a little loop. The loop is 4, 2, 1, and it will repeat forever. Let's try another number. How about 7? 7 is odd. 3 times 7 is 21, plus 1 is 22. 22 is even. Half of that is 11. 11 is odd. 3 times 11 is 33, plus 1 is 34. 34 is even. Half of that is 17. 17 is odd. 3 times 17 is 51, plus 1 is 52. 52 is even. Half of that is 26. Half of 26 is 13. 13 is odd. 3 times 13 is 39, plus 1 is 40. Half of 40 is 20. Half of 20 is 10. Half of 10 is 5. And from 5, we know the way. 5 goes to 16, then 8, then 4, then 2, then 1. It ended at 1. Again, you can try this with any number you can think of. Try 12. Try 19. Try 27. If you try 27, you're in for a long ride. The number will soar up into the thousands before it eventually finally starts to fall back down. But it does fall. It eventually hits 4, then 2, then 1. Here's the question. The simple, frustrating question. Does every number, every single positive whole number, eventually lead to 1? This question is the Collatz Conjecture. A conjecture is a statement in mathematics that is believed to be true, but has not been proven. It's a powerful, well-supported guess. This particular guess has been around since the 1930s. A German mathematician named Lothar Collatz came up with it, and for nearly a century, nobody has been able to prove it. Nobody has been able to disprove it either. It seems like it should be easy. The rules are so simple a child can understand them. You are just dividing, multiplying, and adding. But this problem has resisted the efforts of the most brilliant minds in mathematics. It is a monster hiding in plain sight. The numbers in a Collatz sequence are sometimes called hailstone numbers. This is a good analogy. Think of a hailstone in a thundercloud. It gets pushed up by the wind high into the atmosphere, where it gets bigger. Then it gets heavy and starts to fall. Then another updraft catches it and pushes it even higher. Up and down, gaining and losing altitude, until it finally gets heavy enough to fall to the earth. The numbers in this problem behave just like that. The multiply by 3 and add 1 rule is the updraft. It sends the number soaring. The divide by 2 rule is gravity. It pulls the number back down. For any number we've ever tested, gravity eventually wins. The number falls and falls until it hits that final ground of 4, 2, 1. But the conjecture is not about the numbers we have tested. It's about all of them. All of them, out to infinity. And that's the problem. Just because it's true for the first trillion or the first quintillion numbers doesn't mean it's true for all of them. There might be some monstrously large number out there that behaves differently. How could the conjecture be false? There are really only 2 ways. First, there could be a number that doesn't fall back down. Its sequence might just go up forever. It would get caught in an endless updraft, always getting bigger and bigger, shooting off toward infinity. We have never found such a number. As the numbers get larger, the divide by 2 step tends to happen more often than the multiply by 3 and add 1 step. So there seems to be a general downward pull, but nobody has been able to prove that this downward pull always wins. Maybe there is some special kind of number with some unknown property that can escape this pull. Second, there could be another loop. We know about the 4 to 2, 1 loop. It's the end of the line for every number we've ever tried. But what if there's another one? A different cycle of numbers that repeats on its own and never gets down to 1. Maybe there's a chain of 1,000 numbers that just loop back on themselves, or 1,000,000. Mathematicians have searched for other loops. They've proven that if another loop exists, it must be incredibly long, involving thousands, if not millions, of steps. And the numbers in it would have to be astronomically large, but we haven't been able to prove that no other loop exists. The possibility is still out there, however faint. The problem got its name from Lothar Collatz. He was born in 1910. He supposedly thought about this problem in the 1930s, but he didn't publish it widely. He just shared it with his colleagues. He would pull people aside at conferences and pose this simple little puzzle. From there, it spread like a rumor through the mathematical community. In the 1950s and 60s, it started to gain more traction. It popped up at different universities. At Syracuse University, it was worked on so much that it became known as the Syracuse problem. At Yale, a mathematician named Shizuo Kakutani was fascinated by it. He spoke about it so often that his colleagues said he was obsessed. He joked that the problem was part of a conspiracy by the Soviet Union to slow down American mathematical research. It was a joke, but it captured a real truth. The problem is a time sink. It's a black hole. You start playing with it, thinking you see a pattern, a new angle, hours disappear. For days. You make no progress. The great mathematician Paul Erdos, a man who solved more problems than almost anyone in history, once said of the Collatz Conjecture, mathematics may not be ready for such problems. This is a powerful statement. It suggests that our current mathematical tools, the very way we think about numbers, might be too primitive to crack this nut. It's like trying to build a skyscraper with stone tools. We might need a whole new kind of mathematics to even begin to make a dent. So why is it so hard? The difficulty seems to come from the way the problem mixes two different kinds of math. The multiply by 3 and add 1 part is arithmetic. It's about addition and multiplication. The divide by 2 part is about number theory. It's about the property of being even or odd, of being divisible by 2. These two branches of math don't always play nicely together. The rules of the Collatz game force them to interact in a way that creates chaos. The process is deterministic. There is no randomness involved. If you start with the number 7, you will always get the exact same sequence. Always. Yet the sequence itself looks random. It's unpredictable. You can't look at a giant number and predict how many steps it will take to get to 1. You can't predict how high it will climb before it starts to fall. This disconnect between a simple deterministic process and a chaotic, unpredictable output is at the heart of many deep mathematical problems. It feels like we are looking at the weather of numbers. We know the rules of physics that govern the atmosphere, but we can't predict the exact path of a hurricane a month from now. Over the decades, computers have become a key tool for investigating the problem. In the early days, mathematicians would check numbers by hand or with mechanical calculators. Now, we use powerful computers to check numbers by the billion. We have verified the conjecture is true for all numbers up to a mind-bogglingly large value. We're talking about numbers with more than 20 digits. Every single one of them has eventually fallen to 1. This is strong evidence. It makes us feel more confident that the conjecture is true. But it is not a proof. In mathematics, 1,000,000 examples are not a proof. 1,000,000,000 examples are not a proof. You need to provide a logical argument that shows it must be true for all numbers, without exception. A proof must cover the numbers you haven't checked, the numbers that are too big for any computer to ever reach. Imagine you have a big bag of marbles. The conjecture says that every marble in the bag is red. You start pulling them out one by one. The first is red, the second is red. You pull out 1,000,000,000,000 marbles, and they are all red. You would feel very, very confident that all the marbles are red, but you haven't proven it. There could still be a single blue marble hiding at the bottom of the bag, which is infinitely deep. The computer checks are like pulling marbles from the bag. They are encouraging, but the job is not done. So, what progress has been made? While a full proof remains out of reach, mathematicians have managed to chip away at the edges of the problem. They have discovered some things. For example, they have shown that a very large percentage of numbers do, in fact, eventually reach 1. This sounds a bit strange. How can you prove it for a percentage of an infinite set of numbers? It's a concept from a field called number theory, which allows mathematicians to talk about how dense certain types of numbers are. The biggest breakthrough in recent times came from a mathematician named Terence Tao. He is widely considered one of the greatest living mathematicians. In 2019, he published a paper on the Collatz Conjecture. He didn't solve it, but he proved something remarkable. He proved that the conjecture is almost true for almost all numbers. That sounds like a weasel-worded statement, but in mathematics, it has a very precise meaning. His result means that for pretty much any starting number you choose, even a ridiculously huge one, its path will eventually drop below any threshold you can name. It might not get all the way to 1, but it will get close. It proves that a number can't just go up to infinity forever. It has to come down. It might not come all the way down to 1, it might get caught in another loop, but its upward journey cannot be endless. This was a huge deal. For the first time, a major piece of the puzzle had been put in place using modern, powerful mathematical techniques. Dow's work showed that the problem wasn't completely untouchable. It showed that our mathematics might, just might, be getting ready for it after all. But it's a partial result. The final step proving that it always gets all the way down to 1 is still missing. And it seems to be the hardest step of all. The Collatz Conjecture has a strange dual identity. On one hand, it's a serious and deep mathematical problem attracting the attention of top-tier researchers. It's connected to fields like dynamical systems and ergodic theory, areas of math that study how systems change over time. A solution would likely introduce new ideas and new techniques that could be applied to other problems. On the other hand, it's a folk problem. It's a hobby for amateurs and enthusiasts. Anyone who can do basic arithmetic can start exploring it. You can write a simple computer program in a few lines of code to generate Collatz sequences. You can spend an afternoon charting the path of different numbers, watching them rise and fall. This accessibility is part of its charm. It feels like a problem that belongs to everyone, not just the experts. But this accessibility is also a trap. Because it's so easy to state, many people over the years have believed they have solved it. Mathematics departments at universities regularly receive manuscripts from amateur mathematicians claiming to have a simple proof. These proofs are almost always flawed. They contain a subtle logical error, or they make an assumption that isn't justified. The problem's simplicity is deceptive. It lures you in, makes you think you understand it, and then reveals its true, monstrous depth. There is a lesson in this. The problem shows that simple rules do not necessarily lead to simple behavior. In fact, they can lead to unimaginably complex behavior. We see this not just in math, but everywhere in the world around us. Think of the simple rules of physics governing how particles interact. From those simple rules, you get the entire complexity of the universe, galaxies, stars, life, consciousness. Think of the simple rules of biological evolution. From those rules, you get the incredible diversity of life on Earth. The Collatz Conjecture is a perfect miniature example of this profound principle. It's a pocket-sized universe of complexity. What would it mean if someone finally solved it? If someone proved the conjecture is true, the proof itself would be the main prize. The mathematical world would celebrate not just the answer, but the new methods used to get there. It would be like a new key had been forged, a key that could potentially unlock other stubborn problems. The conjecture itself isn't directly applied to building bridges or programming computers. Its value is in the journey, in the struggle to understand it, and in the new mathematics that might be born from that struggle. And what if someone proved it was false? That would be even more shocking, in a way. It would mean finding a specific number that either goes to infinity or gets stuck in a new loop. Finding that number would be a monumental achievement. It would be like discovering a new species of animal that everyone thought was a myth. That number, that counterexample, would be a mathematical celebrity. People would study it for decades, trying to understand its properties. Why does this number behave differently from all the others? What is special about it? Its existence would tell us that the world of numbers is even stranger and more mysterious than we imagined. But for now, we are stuck. We are in the same place we have been for decades. We have a simple question, and we have no answer. The problem sits there, quietly mocking us. It is a testament to the limits of our understanding. It reminds us that there are still dragons on the map, even on the familiar map of the whole numbers we learn about as children. The search for a solution continues. Some mathematicians work on it directly, others work on problems that are related to it, hoping to build up the tools that will one day be used to tackle the main beast. Computer scientists continue to push the boundary of how many numbers have been checked, expanding our library of evidence. And amateurs continue to play with it, drawn in by its simple charm, dreaming that they might be the one to spot the simple pattern that everyone else has missed. The Collatz Conjecture is more than just a math problem. It's a story. It's a story about the nature of numbers, about the difference between simplicity and complexity, and about the enduring power of a simple question. It's a story about human curiosity and our relentless desire to know. It's a detective story where the crime is a logical puzzle and the clues are scattered across the infinite landscape of numbers. And it's a story that, as of today, still has no ending. We don't know if the hero our understanding will win, or if the villain, the problem's complexity, will forever remain undefeated. All we can do is keep trying, keep thinking, and keep following the numbers wherever they may lead. up and down, hoping that one day we'll finally understand why they always seem to come home to one.